Hello, my name is John Cody. I'm an engineer from Vancouver, Canada. Today I'll be talking about the quadria of the projective quadrangle in universal hyperbolic geometry. So we're in the setting of projective geometry. We have on the left-hand side, we have universal hyperbolic geometry depicted by this diagram right here. And on the right-hand side here, we have elliptic or spherical geometry depicted by this diagram, or this figure. Universal hyperbolic geometry uses the following quadratic form: x squared plus y squared minus z squared equals k. So there's a minus sign here. And elliptic or spherical geometry uses the quadratic form x squared plus y squared plus z squared equals k. And what we will show is that the quadria of the projective quadrangle is given by the following formula. And it's the same. There's a pair of quadratic equations that are compatible, equation 1 and equation 2 here. These are two compatible equations, and they have a unique common solution given by this expression here. Now, this equation is valid in both the hyperbolic geometry setting, the universal hyperbolic geometry, and it is also valid in the elliptic geometry setting. It's the exact same equation. And we showed in a previous video that this was true for the case of universal hyperbolic geometry that use this quadratic form, x squared plus y squared minus z squared. And in this video, we're handling the case of, we'll show that it's true in the elliptic or spherical geometry, which uses the quadratic form x squared plus y squared plus z squared equals k. So there's a plus sign here. So in both of these settings, in hyperbolic geometry and elliptic geometry, in projective hyperbolic geometry and projective elliptic geometry, the exact same equations are valid. Okay, so I'll follow the same line of reasoning that was done in the universal hyperbolic geometry case for the elliptic spherical geometry. So we start off by reminding you about the quadratic compatibility theorem, which is theorem 1 in the book Divine Proportions by Norman Wildberger. And it states that the quadratic equations x minus p1 squared equals r1 and x minus p2 all squared equals r2, these two quadratic equations are compatible precisely when this expression is true. p1 minus p2 squared minus r1 plus r2, all of that squared on the left-hand side is all squared, is equal to 4 times r1 times r2. And when, in the case when p1 is not equal to p2, when p1 is not equal to p2, then there is a unique common solution given by x. The common solution of these two quadratic equations is x is p1 plus p2 all over 2 minus r1 minus r2 over 2 times p1 minus p2. So what we do is we create a Mathematica function for the unique common solution of the pair of compatible quadratic equations. So call this equation right here. We're expressing it in Mathematica right here. So we're going to pass in p1, r1, p2, and r2. So that's p1 and r1 and p2 and r2 from the two quadratic equations. Excuse me. So the equation x is p1 plus p2, same here, p1 plus p2 all over 2 minus r1 minus r2, all divided by 2 times p1 minus p2. So this is the Mathematica equation for that. We're in a Mathematica notebook, Wolfram Mathematica. And the quadria A is given by this will give you the common solution here. So we're going to pass in for P1 and R1 and P2 and R2. So P1 is this quantity right here, Q1, Q2 plus S2 plus Q3 plus Q4 times S4. So here are our two original quadratic equations, and they have the form expressed in the quadratic compatibility theorem. So this quantity here is P1. This quantity here is, on the right-hand side, is R1. The quantity right here is P2, and the quantity here is R2 from the quadratic compatibility theorem. So when we plug those quantities into this equation for x, we get A, and here it is, the quantity A. Okay, so here's the Quadria of the projective quadrangle theorem. It says, suppose A1, A2, A3, and A4 are distinct projective points with quadrants as Q1 is the quadrants between A1 and A2, Q2 is the quadrants between A2 and A3, Q3 is the quadrants between A3 and A4, and Q4 is the quadrants between A4 and A1. And spreads, S1 is the spread between line A4, A1 and line A1, A2. S2 is the spread between A1, A2 and line A2, A3. S3 is the spread between A2, A3 and line A3, A4, and S4 is the spread between line A3, A4 and line A4, A1. And Quadria A, then the quadria of the projective quadrangle is the common solution of the following pair of quadratic equations. And here are the two quadratic equations that we started off with. Okay, so again, we have in universal hyperbolic geometry, you had these four projective points, A1, A2, A3, and A4, with quadrants between A1 and A2 is Q1. Similar, Q2 is the quadrants between A2 and A3. Q3 is the quadrants between A3 and A4, and Q4 is the quadrants between A4 and A1. And the spread, S1 is the spread between this line. Here's S2, this is S3, and this is S4. And similarly, in elliptic or spherical geometry, you have projective points A1, A2, A3, A4 on the surface of the sphere. So the projective points are the lines through the origin, and they are these points on the surface of the sphere. So they have quadrants and spreads as similar to the universal hyperbolic geometry case. So you can draw, there's a line connecting A1 and A2, there's a line connecting A2 to A3, a line connecting A3 and A4, and a line connecting A4 and A1. A line, it consists of like a plane through the origin. And similarly, there's spreads here. So there's a quadria for there's a quadria which comes about from these four projective points, A1, A2, A3, and A4. And that's what the quadria of the projective quadrangle theorem states. So the proof of this theorem, the quadria of the projective quadrangle theorem, employs the quadratic compatibility theorem. So we show that equations 1 and 2 above are compatible since they meet criteria for being compatible by the quadratic compatibility theorem. So we just have to show these two equations are compatible. So, and that they are compatible from the quadratic compatibility when this equation or statement is true. So the left-hand side here is equal to the right-hand side. So P1 minus P2 squared minus R1 plus R2, all of that squared, when that is equal to 4 times R1 times R2, then these two quadratic equations are compatible. And that's what we'll show. So here we have P1 minus P2 from the criteria compatibility check. On the left-hand side, we're going to pass in P1, R1, P2, R2. This is a function we're creating, and it's given by P1 minus P2 squared minus R1 plus R2, all of that squared. And the compatibility check on the right-hand side, we pass in the same 4 parameters as 4 times R1 times R2. So what we'll do is the left-hand side, we'll create a variable called LHS for left-hand side, and we're going to call this function compatibility check left-hand side, and we're going to pass in these quantities R1, P2, and R2 from this expression here, these 2 equations. And when we do that, we get expression. And similar on the right-hand side, we're just going to call this function. We're going to call this function with P1, R1, P2, and it gives, and we'll call that the right-hand side, the variable RHS, and that gives this expression here. Next, we expand out the left-hand side. This one here is a quadratic. It's a square. So when we expand it all out, we get this variable left-hand side expand E. LHSE is left-hand side expanded. We're calling the expand function of Wolfram Mathematica, and we're going to pass in our variable LHS. And when we expand it all out, we get this expanded quadrances and spreads. Similarly, we're going to do the same, and we're going to expand the right-hand side and get the variable right-hand side expand, which is this one here, in quadrances and spreads of the quadrangle. And then we're going to get the result, which is the left-hand side minus the right-hand side. And when we do that, we get this expression in the quadrances and spreads. Okay, and next we're going to substitute in, for each of the quadrances and spreads, we're going to substitute in the quadrants and spreads in terms of the points A1, A2, A3, A4. So here we have projected points A1, A2, A3, A4. A1 is x1, y1, A2 is x2, y2, z2. A3 is x3, y3, z3. A4 is x4, y4, z4. And here we're defining 3 functions. The join of 2 points, j of A1 and A2 is given by this expression. Now we're using the quadratic form for spherical geometry in this join expression. Similarly, for the quadrants between 2 points, A1 and A2, we're using the quadratic form for elliptic geometry. So there's a plus sign here, and a plus sign here. And similarly, spread, we're using the quadratic form of elliptic geometry, and we get this with the plus sign here, and a plus sign here. For hyperbolic geometry, we had negative signs here, but for elliptic geometry, we use a plus sign. So we're going to calculate the quadrants between the points. So the Q1 is the quadrants between A1 and A2. Q2 is the quadrants between A2 and A3. Q3 is the quadrants between A3 and A4. And Q4 is the quadrants between A4 and A1. So we're calling this quadrants function for the elliptic, in the elliptic geometry case. And that gives us these quantities. Notice the plus signs here. So this is Q1, this is Q2, this is Q3, and this is Q4. Similar. Now, next we're going to calculate the lines L1, L2, L3, L4, which L1 is the join between points A1 and A2. L2 is the join between points A2 and A3. L3 is the join between points A3 and A4, and L4 is the join between points A4 and A1. So this is L1, this is the expression for L2, this is the expression for L3, and this is L4. Next, we're going to calculate the spread between the lines. So S1 is the spread between line L4 and L1. S2 is the spread between L1 and L2. S3 is the spread between L2 and L3. And S4 is the spread between L3 and L4. And we get these expressions. Okay, next, So the next cell, we're going to substitute in the values. So now we have when we took the left-hand side expanded minus the right-hand side, we got this long expression in the Q's, and then the quadrances and the spreads. Now we have the quadrances and spreads in terms of the projective points x1, a1, a2, a3, which is points in terms of like x1, x1, y1, and z1, x2, y2, and z2, and so forth. So we're going to substitute those values in here. We're going to factor that. And when we factor it, we expect to see that the left-hand side minus the right-hand side should be equal to 0. So, and that's what we see down here. When we do that, it takes like quite some time to do the calculation in the Mathematica notebook. So a result of 0 indicates that the criteria for compatible equations in the quadratic compatibility theorem has been met. And that's what we get. So when we get a result is the factor of RES, and that's 0. So what we have done in this video is we have proved that the following two quadratic equations in A are compatible in the elliptical spherical geometry. So these two quadratic equations in A are compatible. So in the next video, what we'll do is we're going to, from the quadratic compatibility theorem, we're going to compute the value of A and then substitute it back into one of these two equations and prove that they're true also. Okay, thank you for your attention.